the Doctor of Science from Ukraine. I worked at the KTH Royal Institute of Technology in Stockholm, and then now I am working at the Uppsala University in Enström Laboratory. And let me introduce to your attention my presentation, Development of a Statistical Thermodynamic Model for Calculation of Self-Diffusion Parameters in Metals. The development of material science in the coming decades is one of the main driving forces of the new scientific and technological revolution, which is causing significant changes in mechanical engineering and production, construction, and agriculture, military equipment, and everyday life. Diffusion is the most important transfer process of substances and masses in metals. The theory of diffusion is...
I cannot hear you.
You can hear me? Excuse me, can you hear me?
Yes, Professor, we can hear you clear.
I hear you.
Okay, thank you. I will continue.
1 minute, Professor. Maybe Professor Agnes and Xiang Liu Li, maybe there is some problem in your system. Can you check it, please?
Okay. I will continue. The theory of diffusion is solid based on the fundamental concepts of physical kinetic and non-equilibrium thermodynamics is one of the most important branches in material science. Description of the vacancy mechanism of self-diffusion in metals has a significant meaning for this theory. The aim of this work is to develop a statistical thermodynamic model for the self-diffusion in metals and apply it for calculations the diffusion coefficient of atom in metals and alloys. There are different mechanisms of diffusion, but most important from them is interstitial diffusion and vacancy diffusion. We can see on this illustration. This illustration with artificial intelligence. Vacancy migration is the dominant mechanism behind atomic transport equal self-diffusion in mass metals and alloys, and is of a fundamental mechanism of solid phase transformation, nucleation, and defect migration. The atomic theory of diffusion has an expression for the pre-exponential factor of self-diffusion that depends from the square of the distance between two atomic positions. Equation 1a. The relation between the mean square displacement and diffusion coefficient is expressed as equation 2.
You don't see your equations.
Yes, equations 2a. And have the same ratios, where d is the dimension, the mean square displacement of an atom at time t. However, the main driving force in the theory of diffusion is the gradient of chemical potential of the component of the system. This should be considered when finding equation for the self-diffusion coefficient in metals. In statistical thermodynamics equation describing diffusion of hydrogen and carbon in metals, I developed and it have been known. Similarly, it is of undoubted scientific and methodological interest to also derive the corresponding diffusion equation for the self-diffusion of atoms in metals. Vacancy can be thought of as statistical gas diffusing in the periodic potential produced by metal atoms. And so this system offers an excellent implementation of the statistical thermodynamic concepts of energy side distribution. This is vacancy as a gas in the crystal lattice metal. In work 1, I developed statistical thermodynamic model of atom diffusion in the crystal lattice of a metal. The number of diffusive atoms in each state was determined by the Boltzmann distribution. First of all, I obtained the dependence of the diffusion flux on the chemical potential gradient, which is on the basis of non-equilibrium thermodynamic and phase field modeling. First. And second, I derived the expression for the pre-exponential factor of the diffusion coefficient from ab initio calculations. This one, this guy. This statistical model was implemented for the impurity atom diffusion in the crystal lattice of metal. On the scheme, on the figure 1, we can see a scheme of diffusion of vacancies in a statistical thermodynamic model. Gray sphere symbolize metal atoms, and empty circle symbolize a vacancy. The equilibrium concentration of vacancies is determined by the formation energy EF. Expression 1, where T is the temperature, K is Boltzmann constant. The self-diffusion coefficient is given by a similar expression. Expression 2, where EM is the migration energy or diffusion barrier. The entropy of formation as well as of migration also enters this expression, but the most important term, in particular at lower temperature, is the energy of formation and migration. We take in account the number of vacancies and equal number of diffusive atoms in each state was determined by the Boltzmann distribution 2. This expression 3. Having performed calculation for the diffusive flux of vacancies similar to the calculation of the carbon atom diffusion, has been found the total diffusion flux of vacancies in the positive direction of the x-axis. Expression 4. Where we have this constant chemical potential of vacancies and its gradient. There is the interplanar distance. H is the Planck constant. M is the atom mass of metal. Substituting the expression 5 and 6 in the equation 4, we find the common diffusion flux of vacancies in solid solution. Expression 7 and 8. This is a basic expression. Expression 8 of the developed statistical model significantly difference from the expression used in simple molecular dynamics. The interplanar distance they enter in this expression is first degree, but this formula assumes the dependence of d0 from the square of the temperature and from physical constant. For practical calculation, self-diffusion and alloys, a statistical calculation model, SCM, has been developed. It includes first principle calculation of the diffusion coefficient according to a statistical model, and physical-chemical calculations of activation energies for elements, metals and basic metals and silicon. The diffusion coefficient can be calculated by the formula following from expression 8. This one, expression 9. Where Q eta is for every I metal, and D0 depends from the square of temperature. For metals with the activation energy of diffusion or migration and diffusion is still unknown, we propose to use the correlation relationship between the activation energy of self-diffusion and the melting temperature of the I element Ti. Expression 11. K is the Boltzmann constant, K0 is the constant coefficient. This guy for the self-diffusion was selected from the correspondence of the activation energy calculated using formula 11 with relabeled data from work on the self-diffusion in iron. Ka is the coefficient considering amendments for element E made on the basis of experimental data from work on the self-diffusion in metals. This is our theoretical method and calculated method. Calculated data on the value of the self-diffusion coefficient in metals in comparison with the experimental data I show on the figure 2. Blue square show calculated value of the eta according to SCM-model with the temperature 1000 Kelvin. Brown circle I experimental, some experimental value. Figure 2 shows that the calculated value of the self-diffusion coefficient for metals agree well with the experimental value that would be expected. In this section, a comparison is made on the SCM calculated data and the experimental data on the diffusion coefficients obtained early in the corresponding work and represented by the Arrhenius equation. This experimental data. Two different Arrhenius equations. The SCM-model provides a smaller deviation from the pre-exponential value of the coefficient for metals than the experimental value of Arrhenius, of well-known Arrhenius equation for these basic metals. Temperature dependence of self-diffusion coefficient and alpha iron and gamma iron present on this slide. Comparison of calculated data on self-diffusion coefficient value in alpha iron present on the figure 4. Red circle show calculated value from the SKM model. And green triangle and blue rhombs represent calculated value from the different well-known Arrhenius equations. From figure 3 and 4, we can see good agreement between the value calculated using the Arrhenius equation and the SKM model. For gamma iron, the value of all three equations used for the analysis vary practically identical over a wide temperature range. The SCM model is quite efficient for estimating self-diffusion coefficients in iron. On this slide, we can see temperature dependence of self-diffusion coefficient and important metals titanium and vanadium. For titanium, almost complete agreement with the experimental results and SKM calculated is observed in the low temperature region. For vanadium, very good agreement with the experimental results and SKM calculated have a place in the higher temperature region. Deviations from the Arrhenius law I observed during the self-diffusion in vanadium and titanium, which can also be explained by the proposed SKM model. Similar calculations were performed for two refractory metals, molybdenum and tungsten, and for two low melting metals, silver and copper. In this case, experimental data from two different sources were also taken account for Arrhenius equation. Temperature differences of self-diffusion coefficient in molybdenum and tungsten I show on the figure 7. And for molybdenum on figure 7 and for tungsten, excuse me, on the figure 8. From this figure, it is clear that SKM model fits well at least one experimentally obtained Arrhenius equation. For molybdenum and tungsten, almost complete agreement with the experimental result is observed in the higher temperature region. We can see it on these figures. Temperature differences of self-diffusion coefficient in two low melting metals, silver and copper, we can see on the figure 9 and 10. For silver, there was a very good agreement between the calculated SKM and the empirically validated Arrhenius equation over the entire temperature interval. For copper, calculated value of self-diffusion coefficient were between two empirically substantiated Arrhenius equations. In this case, the accuracy of the value calculated by SKM model was also very satisfactory. And we have this conclusion. A statistical thermodynamic model of the self-diffusion in the crystal lattice of metal has been developed. The direct relationship between the diffusion flux of vacancies and the gradient of their chemical potential in the model has been established. For a solid solution of vacancies in metal, an expression for the coefficient of self-diffusion from the basic principle of statistical thermodynamic has been found. Its magnitude depends on the physical constant, the atomic weight of the metal, the square of the temperature, and the concentration of vacancies in the solid solution. To calculate the activation energy of self-diffusion in metals and simple alloys, a SKM model was proposed that consider energy calculation from first principle, statistical processing of experimental data on self-diffusion of metals, and a physico-chemical model using the correlation relationship between the activation energy of self-diffusion and the melting temperature of metals. Based on the processing of experimental results on diffusion in metals using SKM model, thermodynamic parameters of self-diffusion, activation energy in alpha and gamma iron, titanium, vanadium, molybdenum, tungsten, silver and copper, and other metals were established. The calculations from SKM I compared with the known experimental data on the self-diffusion in iron and metals with a good agreement between the results. This agreement for the given special cases of diffusion is higher than in classical atomic diffusion models. Deviations from the Arrhenius law are also observed during the self-diffusion in vanadium and titanium, which can also be explained by the proposed SCM model. The SCM model for self-diffusion in metals and simple alloys was implemented in the corresponding database, including 43 base metals and silicon. Further development of this model will allow us to take into account the influence of different factors on self-diffusion in iron and alloys, and to calculate the diffusion coefficient for alloying elements in alloys. In the end, I would like to thank conference organizers for this good opportunity to me make my presentation, and thank you, dear colleagues, for your attention.